Okay, here are your explanations of the example problems for Lesson 8 in Chapter 4. Lesson 8 is quadratic functions. So the first thing I want you to do is put a definition of quadratic functions in your notes, and if necessary, put it on your gold sheet. I would definitely recommend that you put at least this much of it on your gold sheet. Now let me talk about this for a minute so you fully understand exactly what we're talking about here. A quadratic function can be written in this form right here: y equals ax squared plus bx plus c. Now what that means is that notice that the variable here and here is the same variable. So we're going to have x, maybe 5x squared plus 2x plus 4 might be an equation. Let's write that down here. 5x squared plus 2x plus 4 might be an equation. Okay? So the reason we use the letter C here is because this is a constant. 4 is a constant. 4 is always 4. These two terms are variable, and they vary based on one input, x. In this case, it's x, so if x was 3, it'd be 2 times 3 is 6. In this case, it's x squared, so it would be, if x was 3, it'd be 3 times 3, which is 9, times 5, so this would be 40. So you can see how things vary, but we have an output of y and one single input of x, and we have a coefficient of x, and the coefficient of x is referred to by the letter a here. So in other words, in this case, the coefficient of x is 5. In this case, the coefficient of x is 2. So the coefficient of x squared is represented by the letter a. The coefficient of x, just x, not x squared, is represented by the letter b. So that's why we have all these letters here, which makes this seem a little bit confusing, but just recognize that if you see something like this right here in problem number 1, this is a quadratic function because it has an output of y equals a variable squared. This is what's different here in regard to quadratic functions as we start talking about squares. It's no longer just y equals 3x. If we had 3x, that would be in this portion, the bx part of the equation. If there's no variable squared, it's not quadratic. Okay, so let's finish up our definition up here. So a quadratic function can be written in this form, as we talked about already, and where a does not equal 0. So in other words, if a was 0, we'd go back to what we had before. If we had y equals 0x squared plus, let's say, 3x plus 4, well, this disappears. This is really just y equals 3x plus 4. And remember, y equals 3x plus 4 is a linear equation. That's y-intercept form. This is the slope-intercept form of a line. We know this is linear because it's a line. That's why a cannot be 0. As long as you have some amount, it could be 1x squared. Now you have the variable, an input squared, and that makes it quadratic. And now lastly, to finish up, the graph opens upward if the coefficient of the variable that is squared is positive. So in this case, I would just call it the coefficient of x squared. If it's positive, it opens upward. If it's negative, it opens downward. Let me show you what that means. Here's an example of a positive coefficient of x squared. So because it's positive, the graph opens upward. The open part of the graph is upward. I will show you the corresponding negative one in the next sample problem, or you can look in your book right now. But let's talk about how they get this graph here. First of all, there's a real simple way for you to do it. You can take this and put it in a graphing calculator, and it will draw this graph for you. This is a quadratic function. You should also understand that you can do it by making a table of values, just like you can plot y equals 3x plus 4, and you can make a table of values and create the line that way. You can do the same thing here where you create this line, this graph, by making a table of values. So we put in an input of -2. Well, if x is -2, then x squared would be -2 times -2, which would be +4 for an output. Put an input of -1 in, and you get an output of positive 1. Negative 1 times negative 1 is positive 1. 0 times 0 is 0. 1 times 1 is 1, and 2 times 2 is 4. So now we have these values for coordinates, so we can plot the point negative 2, positive 4. We moved to negative 2 on the x-axis, and then up to positive 4 on the y-axis, and there's where our point would be, negative 2, positive 4. Notice we have a corresponding value right down here, with positive 2, positive 4 being the point right there. And we would have negative 1, positive 1 would be right here, and that was this one here, and positive 1, positive 1 being right here, and of course we have 0, 0. So once we have these points plotted, and because we recognize that this is quadratic and therefore a curved line, we can plot this like this and this right here. So remember, you need to be able to do two things. You need to be able to create a table of values so that you can get specific points. If you're asked to put this on a graph, you need to have your graph go through this point and this point. We could move further up here, and if we put in negative 3, we would have negative 3, and it would go up to positive 9, and we could put a point there. Positive 3, positive 9, and we could put a point there. And we could be really accurate with the way that we graph this thing. That's one way to do it, is with the table of values. And only as a check, I would make sure that you understand how to take a graphing calculator, put this in a graphing calculator in order to show this. One thing that would be very helpful in regard to understanding how to use a graphing calculator when doing these things is it's a great check. Because, for example, if you graphed this and you didn't notice that this was a negative x when you start doing your, or you did the math here incorrectly, and we'll talk about that in a minute, you might have a graph that looks more like this. In other words, opens up. But this is a negative coefficient, so if you put this in the graphing calculator and graph it, it will show you that this graph opens down because it has a negative coefficient of that variable squared. And that is the power of using a graphing calculator, to check your answers, because it will alert you to silly mistakes like that. So now let's take a look at how they got this information here. Again, we have an equation right here. We put an input in. We're going to start with negative 2. So if we put negative 2 where this x squared is, it would be the negative value of negative 2 times negative 2. Negative 2 times negative 2 is 4, and the negative value of that is negative 4 plus 4 gives us 0. And this is where some kids might have some difficulty with this math here, because we're not real good at adding and subtracting positive and negative numbers, or multiplying them in this case, and we make a mistake, and that's where the graphing calculator will alert you to some of your mistakes. So we should have an output here of 0. Put in negative 1, and we should have an output of 3, and you can see the rest of it here. Remember that whenever you do this math, you should end up with corresponding values. If you put in negative 2 and positive 2, you should end up with the same answer, 0 and 0, in a quadratic equation. This is really important to notice that, because it will help you notice if you make a math error somewhere along here. And then again, we can take a look at this and we can say, I'm going to start here at 0. I'm going to graph this point right here, negative 2, 0. I'm going to go to negative 2 and up to 0, which would be right here as a point. And then we also have one at positive 2, 0. We also have a point at negative 1 and up to 3, positive 1 and up to 3, and here we have a point at 0, 4. So go to 0 and straight up to 4, and you can see our parabola starting to take shape here. We could draw a nice arc down this direction and one down this direction, and we notice that it opens downward because we have a negative x variable. Please press pause and do letter A. Okay, let's take a look at problem number 3. We have a function, first of all, that is d equals 4t squared. So that, remember, that would be just like y equals 4 x squared. We're just using different variables here, and we're doing it for a very good reason, because this function represents the distance, that's why we're using the letter d, in feet, that a race car will travel over t seconds. So t in this case stands for time. So we've got time here, and we've got distance here. The distance traveled is 4 times the time squared. So it's 4 times time times time. Probably a better way to put that would be, it'd be 4 times the seconds times the seconds, with a constant acceleration of 8 feet per second. Graph the function. Again, we could do that by making an output-input table, and that's what we're going to talk about here in a second, and then use the graph to find out how much time it will take for the race car to travel 200 feet. So we have an input of 0 and 0 time. We're obviously going to go 0 because it would be 4 times 0 times 0. That's what this represents here, and it's because we put in 0 for t. Now we're going to put in 1 for t, so it's 4 times 1 times 1, and of course the output there is 4. Then it's 4 times 2 times 2, that'd be 4 times 4, that's 16. You can do the rest of the math yourself here and check these, and recognize that we're going to have these points to graph. So we're going to put a point at 0, 0. There's the point at 0, 0. We're going to put a point at 1, 4. That would be right there. 3, 36. So we put a point right here at 3, and across here at 36. I'm going to put another one at 5, 100. This one's really easy to graph because we've got exactly 5 here and exactly 100 here. So that makes our point there, and we finish out the graph. Once we plot all of those points, we have each of these individual points, we begin to see the graph start to take shape, and then it's time to draw a nice curve right through all the lines as best you can. Now once we have that, they said use that graph that you just created, find out how much time it will take for the race car to travel 200 feet. Well, we should have, right from the start, have recognized that our input was time, and it was in seconds, and our output was d, and that was distance in feet. So our 200 feet is going to be on this axis. We have 180 here, and we're counting by 20s obviously, so this right here would be 200. We read right straight across 200, and right there's our intersection, and from that point we move down here. They say that it is about 7 seconds, and I would say that we can tell that it's probably just a little less than that, so we could say maybe 6.8 seconds. But there would certainly be nothing wrong with an answer of 7 seconds. Now let's take a look at problem number 4, a very similar problem. In this case, we have the function h equals 66/100ths d squared. In this case, d is the miles that you can see from the height of h. This is height in h. So in other words, that because the Earth, remember, is round, if you're standing any particular place on planet Earth, the higher up you get, the farther out you can see. Whereas if I'm right here, I can only see to about here, etc., etc. You get the idea. The higher you are, the further in the distance you can see because of the curvature of the Earth. Okay, so they ask you to graph this function, and then use the graph to estimate how far you could see from a hot air balloon 1,000 feet in the air. So if you get 1,000 feet up in the air, how far can you see? Now remember, in the previous problem, notice that you can look back there and say that, notice that it says that distance cannot be negative. I forgot to explain that. Remember, this would be a quadratic function, so we would have a corresponding side of this parabola, but it doesn't make any sense here. That doesn't make any sense because you don't have a negative distance, so we ignore that. But still remember that this is a parabola. It is the graph of a quadratic function, so it is a gradually curving upward type of scenario, and you need to learn to recognize that. But in this case, I'll say again, all these values make no sense, so we're not going to do that. We're going to take our equation, it's right here, and we're going to put in these inputs. If we put 0 in, we have 66/100ths times 0 times 0, which is, of course, 0. Then we're going to put 10 in, so it would be 66/100ths times 10 squared, or 10 times 10 is 100, so of course our answer is going to be 66. We just dropped the decimal point over 2 places. And again, you can take a look at how they put all these in. You would certainly want to use a calculator here. The way I would do this to put this in a calculator is I would just put in 20 squared. Once you have that number, multiply it by 0.66. 25 squared times 0.66, etc., and you'll get all of these output values. Once you have those output values, it's time to start plotting points. For 0, 0, we're going to put a point right here. For 1066, now notice that they had to determine what their scale was going to be. It's a good idea in this case because you have to fit from 0 to 40 on your input. They decided to count by tens. Actually, they're counting by fives because they're not labeling the ones in between, and they can get everything that they need fitted in here. Now, in this case, on your outputs, you need to fit through from 0 through 1,000, a little over 1,000, in fact. So they decided to count by hundreds, and notice they only labeled every other one, so it's 200, 400, 600, etc. Again, we had a point at 0, 0. Our next point is at 1066. Let's just pick another one at random here. For 30, we're at almost 600, 594. So at 30, we're going to come up here at 30 and stop just short of 600, and that looks pretty close to 594. And again, we're going to plot each of these points, and you can see each of the points plotted here, and then we draw our line as best fit as we can. And then we take a look at the problem they asked us. How about if we're 1,000 feet in the air? Well, feet is on this axis here, and 1,000 is right here. So we move right straight across at 1,000, and we intersect right there. And I'm going to clear this so we can see things better here. And you can clearly see that we end up just shy of our 40 mark here. So they come up with a solution of about 39 miles. So if you were 1,000 feet in the air, you should be able to see, of course, on a very clear day, about 39 miles in the distance due to the curvature of the Earth. Please press pause and do letter B.